Hello everyone, we're back again, working in our notepad top of page 7 in section 3, energy diagrams. In this section, we just take a quick opportunity to catch up some of the notes that we'd been taken before when we were writing exothermic and endothermic diagrams. We know that for a reaction to occur, two molecules must collide with enough kinetic energy in order to break the bonds. If we think about this single replacement reaction, and I know it's a single replacement as we review our patterns of chemical change, we have a compound called compound AB, where A is bonded to B, and it's reacting with an element. Notice that the element is being represented by C in the green molecular atom. And now we have a new element and a new compound form. The pattern of change known as single replacement. Notice that the compound BC is a new bond that is going to form, and the bond that must break is A connected to B. So bonds break through collisions of molecules. And to be a successful collision, they must also have the correct orientation. So in order for compound AB to collide with C, you need a head-on collision, not just a quick breeze by with an improper orientation, but a full force with enough energy to cause bonds to break and new bonds to form. So those two requirements in terms of two molecules colliding with enough energy to break bonds, and the orientation must be correct for them as well. And we can represent that all in action of an energy diagram. In our notes, we're going to draw this energy diagram representing the single replacement reaction, AB reacting with element C. So to do that together, I want you to simply draw an XY axis, and on the Y axis, I want you to label that as energy. And we understand that energy is going to be measured in joules or in calories. As you climb up the y-axis, energy is increasing. And the reaction coordinate, you can even just think about that as time. As time goes by, reactants turn to products. Now, in this specific example, we're going to select a starting point for the reactants, and we'll label the reactants very specifically here as compound A bonded to B, reacting with element C. That all gets placed on the starting position where the reactants are located on our energy diagram. We then draw an energy barrier, a hill known as the activation energy, and we climb down and create the products down lower than the reactant started. So now we're going to place element A and the new compound B connected to C and label those the products. We understand that this is what we refer to as an exothermic reaction. The energy difference between the reactants and products, label that as delta H. Delta H, remember, is heat of reaction. It is a thermodynamic property known as enthalpy. And if you just simply remember H standing for heat, you'll be all set. The enthalpy. This is the difference in energy between reactants and products. There, I wanted to write that down. So the reactants to products. So the delta H in this reaction would be exothermic. We'll know it be where the reactants are of higher energy than the products, so heat releasing. The other part I wanted to be sure to label is what we refer to as the activation energy. And so where the reactants start, to the top of this energy barrier, label that section E sub A. And tell yourself E sub A represents the term activation energy. And we define that as the difference in energy between the reactants and the transition state. And let's focus on what the transition state is as well. Locate the very top of your energy hill. The energy hill, the activation energy, the amount of energy needed for the reaction to occur. I'm going to write that as well. Okay, great. Now you copied that with me. The amount of energy needed for the reaction to occur. It is the energy hill, the energy barrier that separates reactants from products. The transition state is at the very top of this energy hill. Now I want you to think about what the transition state would look like. This is where bonds are breaking and new bonds are forming. And we're writing that down as well. At the top of the energy barrier, this is the site of the collision, if you will. So blowing that up, you have compound A, B, and you have compound C. Those are what we call the reactants. At the top of the energy barrier, you would have a bond breaking between A and B, and a new bond forming between B to C. Let's label those. Bond is breaking between A and B, and the bond is forming between B and C. That's what's happening at the top of this energy hill. Bond breaking, A to B, new bond forming, B to C. And we want to label that as breaking and forming. Transition states cannot be isolated. These are not compounds that can be separated out in your reaction vessel. It's a moment in time where the collision is successfully breaking bonds and new bonds are forming. And then you go on to form the products at the end of the arrow. So the products are assumed to be of lower energy than the reactants in an exothermic reaction. We've written out an energy diagram for a particular compound plus element, making new compound plus element, recognizing that as a single replacement pattern. When we think about activation energy as a measure of how fast a reaction can go, the larger the energy barrier, the higher that energy hill is on our graph, the slower the reaction. So let's take a look at that in terms of a picture. We know that the activation energy is the minimum amount of energy needed to get over that barrier for a reaction to occur. We label E sub A as activation energy. EA is the energy barrier at the height of the reaction rate. So think about that just looking at this diagram. If we have a very large activation energy, that energy barrier that separates reactants from products is quite large. This means that not very many starting reactants will possess enough energy to get up and over this energy barrier. The kinetics, the rate of the reaction, will be very slow. In comparison, if we had an activation energy that was quite small, in terms of reactants going to products, the energy barrier here is much smaller. That means that more and more molecules would have enough energy to cross over that hill, and the reaction would be very fast. So the kinetics of a reaction, kinetics meaning the rate of a reaction, really is emphasized by the size of the activation energy barrier. The higher the activation energy is, the slower the reaction proceeds. The smaller the energy barrier, the faster the reaction can proceed. So activation energy is directly correlated to the reaction rate. Higher activation energy equals slower kinetics. Lower activation energy equal faster rates. And we can see that visually on the graphs as well. The difference in that energy between reactants and products, we label that as delta H. And I want you to just think of that as the heat of reaction. In an exothermic reaction, delta H is always negative. the reactants are of higher energy than the products. So we would know that the products would have stronger bonds as compared to the initial reactants. In an exothermic reaction, heat is being released. That means delta H is always negative, and we're forming stronger bonds in the products than the initial reactants contained. I would also recognize that due to a low activation energy, the rate of reaction would be quite fast. Because see, I could have an exothermic process with a large energy barrier, still having just the difference here of -10 between reactants and products, but with a very large energy barrier, the kinetics would be very slow. So I can get a great indication of the kinetics by looking at the magnitude of EA. I get a nice opportunity to look at the thermodynamics of enthalpy by looking at delta H. We know that delta H is positive for endothermic reactions, meaning the reactants to the products absorbs energy. And when energy is absorbed, delta H will always be positive. You can see this is a very large activation energy on this graph, meaning the kinetics, the rate of reaction, would occur quite slowly. Energy absorbing, remember the transition state is at the top of the energy barrier. That's where bonds are breaking and new bonds are forming. A transition state cannot be isolated. It's just a quick moment in time where molecules collide. When we think of the activation energy in an energy diagram, relating it to rates of chemical change, we can influence the rate of a reaction 3 different ways. The first of those ways is by increasing the concentration of the reactants. Secondly, we can increase the temperature. And third, we'll see, is by adding a catalyst. Let's talk about concentration first, then we'll look at temperature, and finally talk about the term catalyst. If we increase the concentration of the reactants, we're really just increasing the number of opportunities for successful collisions. So the first way to speed up a chemical reaction is to simply add more reactants, increasing the reaction rate by influencing the number of successful collisions. We said the second way we could influence the kinetics to increase the temperature. And this means that you're going to have kinetic energy increase, and therefore the molecules collide more often. Molecules move faster when they're warmer. If their velocity is increasing, by raising the temperature, the molecules move around more, and therefore there's more successful collisions. So we see a direct relationship between kinetic energy, which is directly influenced by adding heat, raising the temperature. Making the molecules move more means more collisions and more success at getting over the energy barrier. Well, let's just practice those 2 ideas. Let's look at this reaction in which ozone reacts with nitrogen monoxide, NO, and it occurs in a photochemical reaction to produce smog. What effect would each of these following changes have on the rate of this reaction? All right, well, let's take a peek at letter A. If we increase the concentration of ozone is O3, ozone. In letter A, it says, let's increase the concentration of a reactant. Well, we directly see increasing the reactant concentration directly affects the kinetics as well. So increasing the concentration of a reactant increases the rate. So what effect would each of the following have on the rate? Letter A, it's making it go faster. If you decrease the concentration of NO, so I'm going to remove some NO, well, there's less collisions, right? Less opportunity for collisions then. And therefore, we could understand fewer collisions, fewer reactants actually making the transition state. That's going to slow the reaction down. If you increase the temperature, more collisions. The molecules are moving around faster. And when I think about that in terms of kinetics, the molecules are moving around more, they're more likely to collide, and therefore the reaction will proceed faster. And the opposite is true. If you decrease the temperature, the molecules start to slow down. And slowing down means fewer collisions, meaning that the reaction will also slow down. We mentioned the third effect on reaction rates would be the effect of a catalyst. Let's define a catalyst as a substance that is used to speed up the rate of a chemical reaction. It's not a reactant, it's not a product, so it sits on top of the arrow. If you look at this example, we have acetylene, C2H4, reacting with molecular hydrogen, H2, going on to form ethane, C2H6. Do you recognize this as a combination reaction? Two compounds, two ingredients influencing to make just one product. So that's what's called a combination reaction. Sitting on top of the arrow is the element palladium. The elemental symbol Pd is palladium. Since it's not a reactant, it's not a product, the catalyst will sit on top of the arrow, just as you see in this example. A catalyst is used and then put back at the end of the reaction. So it's recovered unchanged in the reaction. It does not appear in the product side. It does not appear in the reactant side. Well, let's talk about how a catalyst would work. A catalyst works by changing the amount of activation energy necessary. Really what a catalyst does is provides an alternate pathway for the reaction to occur. Let's suppose in my energy diagram, I start with reactants and I go to the products and I have a very large activation energy. We understand that the larger the activation energy, the slower the reaction. In the presence of a catalyst, I start with the same level of reactant energy, but I provide an alternate pathway of lower activation energy, but I still end at the same amount of product. Notice the reactants start at the same level. The products end at the same level. The only difference is the lowering of the activation energy in the presence of a catalyst. You can clearly see that if you lower this, the reaction will proceed faster. More molecules will possess the minimum amount of energy to get over a smaller barrier than the larger barrier. Uncatalyzed reactions have a very high activation energy, therefore the reaction occurs slower. If the catalyzed reaction lowers the activation energy, the kinetics increase and the reaction proceeds faster. So really, when we're looking at that opportunity, we drew an energy diagram comparing the uncatalyzed reaction to a catalyzed reaction, labeling all the appropriate sections. And that's this diagram into your note pack on page 8. As the energy was lowered, the activation energy was lowered by the catalyst. And the catalyst is used to speed up a chemical reaction. Keep in mind, it is not a reactant, it is not a product, it's simply a substance we add to provide an alternate pathway that requires lower activation energy. At this time, you're going to do a little further reading about reaction rates as it affects the human body and biological catalysts. You're going to read about enzymes, which are nature's catalyst. You'll read about its active sites, and it will give you an idea of a very specific enzyme called lactase. you'll read that ASE are the endings given to enzymes in a biological system. Lactase is the enzyme that works on the sugar called lactose. So at this point, you should pause your video and do your assigned reading. You'll read about the human body, and you have a focus on the environment as well. I'm going to move ahead and look at equilibrium. So I'm now turning to page 9. If you'd like to pause and do your reading first, great. If not, you can come along with me and do your reading afterwards. That's up to you. Our next section talks about equilibrium. Well, so far, we've made an assumption that all reactions go to completion. And when I say go to completion, I could say, for example, a moment ago, we said compound AB reacts with element C to produce a new element, and compound A plus BC. Notice that I had an arrow that only points in the left to right direction. That assumes that we're saying the reaction goes to completion, that 100% of AB plus C converts into A plus BC. An arrow pointing in one direction only will show us a reaction that goes to completion. But oftentimes, reactions don't do that. Reactions are reversible. We have a forward direction, and at the same time, we have a competing reverse direction. I mentioned to you when we first learned about patterns of chemical change that when we have A plus B forming a compound AB, we called that a combination pattern. And we learned that the opposite of that was the decomposition, where AB breaks down into its elements again, A plus B. That we said combinations and decomps are the opposites of each other. Well, oftentimes these are reversible reactions, and we use a double-headed arrow to show reversible reactions. If I see just an arrow pointing left to right, that represents the reaction goes to completion. But oftentimes reactions compete both in the forward and in the reverse direction, and we'll use a double-headed, one pointing to the right and one pointing back to the left. So for example, here's an example of a reversible reaction. Carbon monoxide, written as CO, will react with a water molecule, written as H2O, and notice I have two sets of arrows pointing left to right and then right back to left, a forward direction and a reverse direction. When I say the reaction proceeds forward, the forward direction is pointing from left to right. And when I say the reverse direction, now you're looking at right back to left. So we have a reversible reaction. When this is going on, we say that the system achieves an equilibrium. The term equilibrium means that the rate of the forward reaction is equal to the rate of the reverse reaction. It is a dynamic equilibrium. Those opposite directions are occurring at the same rate. So A plus B is producing product AB at the same rate as it's going back and decomposing. Now, the net concentrations of the reactants and products do not change once you've achieved equilibrium. So once equilibrium is established, the concentrations of reactants and products are stabilized. We can use what's known as an equilibrium constant. That constant gets a letter K, K. Sometimes texts will put EQ after the K to represent the equilibrium constant. This is really just a ratio. The ratio that compares the amount of products over the amount of reactants. It's the relationship between the concentration of the products and the concentration of reactants at equilibrium. And so We represent those concentrations using a bracket. And the bracket, which you see, contains inside whatever elements or compounds are reactants and products. But I want us to note that those are concentration units that are given to us in moles per liter. We will learn that moles per liter is a concentration unit known as molarity. You can go ahead and write that in your note pack now, because that concentration unit will come up again in a further out chapter. Concentration unit of molarity is defined as moles of solute per liter of solution. So when I see a bracket, I want you to know that that's a concentration unit of moles per liter. How many moles of solute are dissolved in liters of solution? So let's take an example using some generic letters. I'm going to write this with you. Let's say we have, in terms of coefficients, reactant A plus reactant B in dynamic equilibrium, making element C and D. I want us to just make a note that this represents the coefficient in my general equation, and this is going to be a reactant called A. And this letter B is going to be the coefficient of whatever number is in front of the reactant I'm calling B. And on this side, of course, we would have the coefficient in front of the product I'm labeling C, and this would be the coefficient in front of the product I'm calling D. Just so we understand what the A's, B's, C's, and D's are representing. The equilibrium constant, KEQ, or simply K, the equilibrium constant is an expression, a ratio, that compares the amount of products over the amount of reactants. Now I said the first product was compound C, so I placed that inside of a bracket to represent its concentration, and I'm going to raise that concentration to the exponent of C. Let me write that again. The coefficients become the exponents on each bracket. So the product called C raised to its coefficient small c. Here is the product D, capital D for the product, raised to its coefficient lowercase d. Products over reactants. The next reactant would be A raised to its coefficient, and the reactant B raised to its coefficient. This is known as an equilibrium expression. The ratio of product over reactants. And we get a number. And it's the magnitude of the number that's interesting to a chemist. There is no unit to report on a K. K is a unitless number. But it's the magnitude of the number that we find interesting. Does it come out really, really big? Or does it come out really, really small? Or is it just a number very close to 1? All of that information gives us an idea about what side of the arrow is being favored in a dynamic equilibrium. Coefficients become the exponents in the equilibrium expression. Shall we try one for real instead of just generic letters? Here's a balanced equation where I see the elemental form of nitrogen, N2, reacting with the elemental form of oxygen, O2, and it's forming 2 molecules of NO. What does the equilibrium expression look like? Well, I would know that it's products over reactants, where the brackets stand for concentration units. Inside the first bracket is the product, NO. And the power with which you raise that to would be its coefficient, and it becomes squared. That's set over the first reactant, which is the elemental form of nitrogen. Since its coefficient is a 1, it's just first order. It's raised to the first power. The same for the elemental form of oxygen. The concentration of NO squared set over the concentrations of N2 times the concentration of O2 is the equilibrium expression for our balanced chemical equation. And we get a number, and that number has no unit associated with it, but it's a number that the size of it, the magnitude, gives us some information about what side of the arrow is being favored. Before we calculate some equilibrium constants, it's really important to become proficient in writing them. Let me ask you to pause the video and write out the equilibrium expressions, K equals, for each of these examples that are balanced chemical equations. Write them out and then come back to the video when ready to check. All right, well, let's take a look at letter A. The equilibrium constant K is going to be equal to, brackets, the concentration of PCl5 set over the concentration of PCl3 times the concentration of Cl2. Since all the coefficients are ones, the exponents are all ones on our expression. Here's letter B. The equilibrium expression would set the concentration of the product sulfur trioxide squared set over the concentration of sulfur dioxide squared times the concentration of O2 to the first power. How about letter C? The equilibrium expression here would take the product of HBr in a bracket squared set over the elemental form of hydrogen to the first power and the elemental form of bromine in the first power. And there's one more to check, KEQ. Here we have the concentration of CHCl3 first power times the concentration of HCl, now that needs to be cubed from its coefficient of 3, set over CH4 raised to the first power and Cl2 cubed. There's the expression for letter D. Products over reactants, where the coefficients become the exponents or the powers with which we raise. We said the KEQ, the equilibrium constant, is just a number, and the magnitude of the number gives us great information. It's what's most interesting to a chemist. What if we get an equilibrium constant that is much greater than 1? Well, notice that the ratio of products over reactants, it would tell us that the products are in greater amount than the reactants. If the numerator is quite large, we get a K that's greater than 1. The bigger and bigger and bigger K is, the more the products are being favored. So notice what we're writing here. The products are quite large. So you see how you're emphasizing that with writing it in big letters. And in terms of reactants, we write those in really small letters. So that K comes out to be greater than 1. The larger the K, the more the products are favored. We would say that the equilibrium lies to the right. On the opposite of that, what if we have a K that comes out less than 1? That tells us that the denominator is larger. And let's write this. In terms of writing products, write that quite small. And then in terms of reactants, write that quite large. So you know that the reactants are being favored. The ratio of products over reactants that comes out less than 1 tells us that the reactants are favored. And the smaller and smaller and smaller K is, tells us that we have more and more and more product, or more reactant. The more reactant we have, let me write that with you. And we would say that the reaction, that equilibrium, is favoring the left side, the reactant side. K constants that are greater than 1 favor the products. The equilibrium lies to the right. Equilibrium constants that are much less than 1 favors the left side. The equilibrium lies to the left and favors the reactants. And what about, you may ask, if we're very close to 1? What if we have the ratio of products over reactants and we come out pretty darn close to 1? Well, what that means is that we have pretty close an equal amount of products and reactants in our reaction vessel. So both the reactants and products are present in similar amounts. And if the K is exactly 1, they're exactly in equal amounts. So in terms of writing your product over reactants, we're using about equal size letters to emphasize they're in equal concentrations. So the number itself, it has no unit, but it's the size of the number, the magnitude of the number that gives us information about the equilibrium, favoring the products for large numbers, favoring the reactants for small numbers, and if it's close to 1, we have an equal amount of both reactant and products in our reaction vessel. Here's an example, just how to read that. It says, here's a balanced chemical equation where the equilibrium constant is part of our equation. It gives us hydrogen reacting with oxygen to make water. And the K constant has a magnitude of 2.9 times 10 to the 82, the 82nd power. Wow, that is a large number. Think about what that means. 2.9, that's got 81 more zeros after it. That product is so far lying to the right because it is truly a very, very large number. You could assume that that reaction actually has gone to completion with that sort of number. To emphasize that this reaction would be favoring this side so much more so as to the other side. And I can show that using an unequal arrow. The reaction lies to the right. The number is extremely large, so the equilibrium is favoring the products. So if K is greater than 1, we know we're favoring the equilibrium to the right. If K is less than 1, we favor the equilibrium to the left. And if it's about 1, we know that we're equal amounts. Ask yourself these. Pause the video and just answer, do we lie to the left or right given these K, EQ values? Well, letter A gives us a very small number. 5 times 10 to the negative 4th power is a very small number. Since K is less than 1, we're favoring the left side of there. The reactants are being favored. The equilibrium lies to the left. In letter B, this is a very big number. This would be 4, 4, 0, 0. That's a lot of zeros there. It's a big number. So that means we're favoring the equilibrium lying to the right, which favors the product side. Letter C is 350. Well, that's also bigger than 1. It's not as big as letter B, but it's certainly a larger number than 1. So it is also lying to the right, favoring the products. And letter D, 0.35, that's kind of close to 1. That's close, approximately. So I'm going to say it's not really favoring right or left, it's lying in the middle, where we have an equal amount of reactants and products. There we go. Lies to the left, then right, and then in the middle. We can calculate equilibrium constants just by being given the concentrations of reactants and products at the equilibrium site. So let's try one out for size. We're going to calculate K for the reaction between the diatomic element A reacting with the diatomic element B to form 2 compound AB. So let's start by writing our equilibrium expression. The concentration of the product, AB, would need to be squared based on its coefficient of 2. set over the concentration of the element A and the concentration of the element B. Those are first powers since their coefficients were 1. Now that we've written the expression, we just simply take the values provided at equilibrium and substitute them into our equation. So the equilibrium constant, well, that would be 0.50 from the AB concentration needs to be squared, set over 0.25 for the concentration of A, and the concentration of B is the same. Let's take the calculator in our hands and type out 0.5 squared divided by parenthesis 0.25 times 0.25. Now make sure you're seeing what I did on the calculator. Make sure you're doing that in a parenthesis to make sure your order of operations occurs correctly. Your key sequence, 0.50 squared divided by parenthesis 0.25 times 0.25, then hit your equal. Without the parenthesis, you'll have an order of operation error in your calculator. Make sure you practice that. You should be getting 4 on your calculator screen, and there's no unit there. If the equilibrium constant comes out to be 4, well, K is bigger than 1, so we know the equilibrium is lying to the right, favoring the product side. That wasn't too bad. You write the expression, and then we simply plug in some examples. What if we're given some molecular art? Here I have an equation, really the same one, but now it's being represented with some molecular art instead of concentration numbers. Let's figure out what's inside this little picture here. Here is an AB. Let's see, 1, 2, 3 molecules of AB are in that picture. I have 1 molecule of B2 and I have 1 molecule of A2. Using the equilibrium mixture, let's calculate K. Well, a moment ago we said K is an expression that compares the concentration of the products over reactants, where the coefficients become the powers with which we raise each 2. So we have AB squared set over A times B. Now let's plug in what we know from the picture. We were given 3 molecules of the compound AB. That needs to be squared. We were given 1 molecule each of element A and element B. So 3 squared over 1 times 1 is 9. With the K so large, we know that we're favoring the right side. So you would just say equilibrium lies to the right. Equilibrium is not spelled right. And therefore you know that the products are being favored. Shall we try another? You try this one. Do it without me and then come back just to check. Using the molecular art, calculate K. Did you notice that this was the reverse reaction? So that when we look at the decomposition, the reverse reaction, these are now the products, so they're on top of the ratio. And these are now the reactants, so they're on the bottom of the ratio. So I rewrote my equilibrium expression, reminding myself that it's products over reactants. Now let's find out what we have. 1, 2, 3, 4 molecules of B. What else do we have? Here's A. 1, 2, 3, 4 molecules of A. And I have 1, 2, that's it, 2 molecules of AB. So I just tallied what was inside the molecular art. Let's use those numbers to calculate our equilibrium. The concentration of A will represent 4, and the same value for the concentration of the element B set over 2 the concentration of AB. Remember, that needs to be squared because of its coefficient. So let's solve that. 4 times 4 is 16, divided by 2 squared, which is 4, comes out to be 4. Since K is greater than 1, the equilibrium lies to the right. There's one more on this page as well. Here we have a synthesis reaction for making ammonia. One molecule of nitrogen reacts with 3 molecules of hydrogen to form 2 molecules of ammonia. Using that equation, our expression would have the product ammonia NH3 squared set over the elemental form of nitrogen to the first power, since its coefficient is a 1. And the elemental form of hydrogen would need to be cubed. There's our expression for this reaction. Now that we have that, we can just plug in the concentration units at equilibrium. The concentration of ammonia is 1.1, and that needs to be squared. The concentration of nitrogen is 0.12, and that's to the first power. And the concentration of hydrogen is 0.36, and that of course would need to be cubed. So think about your key sequence, 1.1 squared divided by parenthesis 0.12 squared, 0.36 cubed, close your parenthesis, equal. Let's try that out together. 1.1 squared divided by parenthesis 0.12 squared times 0.36 cubed. Close your parenthesis, equals. Now, if you want to see that written out just an even further step, we could do this together. We could do 1.1 squared divided by 0.12 squared times 0.36 cubed, just to be sure that you're hitting your keys correctly. So I want to hit it together slower. 1.1 squared, that's 1.21. And then I will hit 0.12 squared, and that gives me 0.0144. And I can hit 0.36 cubed, and I get 0.046656. If you're unsure how to cube, this is how I did it. I hit 0.36, and I used my caret key on my calculator. Do you see that little caret key, the little arrow pointing up? That's caret key. And you could hit cubed that way. And that's how I hit it. 0.36 caret key 3. And now I have that 0.36 cubed as 0.046656. Now I could say, just to keep simplifying, just to show the algebra, just in case you're unsure, I don't mind over-explaining. 0.0144 times 0.046656 inside the parentheses now is 6.718, I'll round a little bit, times 10 to the negative 4th power. So that was me just simplifying inside the parenthesis. Now I can do 1.21 divided by that previous answer, and that's how I found 1801 as my answer. Now all of that can simply be done on your calculator. I just wanted to show the algebra for those who wanted to see it worked out in detail. Here's my final answer. Wow, that's big. The equilibrium lies to the right, where products are favored. That's a really big number from what we've been working with. There's a next set for you to practice. I'm going to encourage you to work on page 12 and come back to the video when you're ready to check. Page 12 will finish this section on concentration units used to solve for equilibrium constants. Welcome back. Well, let's take a peek at letter A first. The equilibrium expression will need to be written out by taking the concentration of the products, which is carbon dioxide and hydrogen. They're both to the first power since these coefficients are ones. Set over the concentration of the reactant, CO, and the reactant, water. Now here I'm given those concentration units right here. So this, I hope you figured that out. These are the concentration units for this problem. The concentration units for this problem were given below. So let's find out our values. First one I want is CO2, just because that's written first. So the CO2 concentration, 0.0164, times the concentration of the hydrogen, 0.0164, those are the same number, set over the reactant, 0.0236, and the water, 0.00240. Let's simplify that ratio and get a number. 0.0164 times 0.0164 equals, divided by parenthesis, 0.0236 times 0.00240, close parenthesis, equal. And my value came out to 4.75. Looks like we have 3 sig figs, so I should keep maybe one more. 4.74, and then it says 85, so I'll round. 4.749 is our K constant. So that is a number bigger than 1, so it is lying to the right, favoring the product side. B. Letter B gives us an expression where the product of N2O4 is set over the reactant NO2, but that needs to be squared from its coefficient of a 2. The concentration of the product N2O4 is 1.26, and those are molar units. Capital M equal molar, molarity, which is moles per liter. A concentration unit 1.26 set over 0.0076 molar units, and that needs to be squared. Let's see what we find. 1.26 divided by 0.0076 squared. Wow, that's a big number. 21814.4, and it has even more numbers after that. Let's work that into 3 sig figs, and I'll do so by writing 21800, no decimal point, so those zeros do not become significant, but I still have the correct magnitude, how large the number is. That means we're lying to the right, and I'm going to capitalize that because that's a really big number. What about this question? How did you do? Well, this is saying A2 plus B2 makes 2AB, and the equilibrium constant is given to us as 4. So that expression would take AB squared over A and B, those diatomic elements. Is this reaction at equilibrium? And if not, which direction would it need to proceed to achieve equilibrium? Oh, well, let's figure out what's in here. I have 1, 2, 3, 4 molecules of A, and I have 1, 2, And that's it. 2 molecules of B and 1, 2, 3, oh, here one more, 4 molecules of AB. So let's calculate what we have so far. And it's not really sure if we're at equilibrium, but let's calculate what these numbers give us and compare. So the AB we know is 4, and that would need to be squared, set over 4 to the first and 2 for the next reactant. So I used this expression. The concentration of AB is 4. That needs to be squared, set over A times B. Well, let's hit that. What do we get? 4 squared divided by parenthesis 4 times 2, which is 8. This gives us a number of 2. And I'm going to just call this Q. I'm going to tell you that Q is going to stand for the reaction quotient. Quotient means to divide, right? And so I'm just dividing. I'm not going to call it K because K would assume we're at equilibrium, and we're not, so I'm just going to call it Q. The letter just stand for the quotient of products over reactants. So if the equilibrium tells me it should be 4, if K is equal to 4, and right now I'm at 2, I need my number to be bigger, right? Q, whoops, I should capitalize that. My reaction quotient is smaller than K. That means I am not at equilibrium yet. If I were at equilibrium, I would have gotten a 4, but I only got a 2. How do I get 2 to turn into 4? Well, I need to shift the reaction right. And when I make it to the right, I make more product. And when I make more product, the top number gets bigger, and Q will eventually turn into a bigger number, like 4. When K is at 4, but Q, the reaction quotient, only gave me the number of 2. I am not at equilibrium because they're not the same. So therefore, I'm not yet there. And therefore, it asks which reaction would, which direction would it have to proceed? And our action is it has to proceed to the right to make more product. That this reaction is still not yet achieved equilibrium. It needs to shift to the right to get that number 2 to become bigger like the number 4. All right, let's try that again. Here's an equation where A plus B forms C plus D. And when it's at equilibrium, the constant comes out to be 8. Let's determine if we're at equilibrium, and if not, which direction should it proceed to achieve equilibrium? We've got some counting to do. The light blue is an A. How many of those do you see? I only see 1. How about B? The B's are the reds. 1, 2. All right, I see 2 of those. How many green letter C's? 1, 2, 3, 4 of those. And how many D's? The dark blue? 1, 2, 3, 4, 5. So our equilibrium expression would have the concentration of C times D set over the concentration of A times B. Let's put in those numbers and see where we're at. The letter C was given to us as 4. The element D was given 5. The element A is a 1. And the element B is a 2. Whoops, I wrote B. Let's solve for that ratio and come up with a Q, right? The equilibrium quotient. 5 times 4 is 20. and I'll divide that by 2, and we get a number 10. I'm going to call this the quotient. Q is going to stand for quotient. Just a quotient is a divide by, right? It's a ratio. And that ratio gave us product over reactants. Compare if Q is 10 and the equilibrium constant is 8, Q is too big. Right? So I'm not at equilibrium. These are not the same number. But I have Q too big. So when Q is too big, we need to proceed to the left to make it become smaller. Reaction must shift to the left. So Q becomes smaller. Right now we have too much product, and too much product makes that ratio come out too big. If it's too big, we need to consume the product, and we do so by shifting this direction, using up the product and making more reactant. Shift to the left to achieve equilibrium. How'd you do? Oh, I bet you're doing great. These aren't so bad. Our last topic on Le Chatelier, I'm going to take a little break in recording. Perhaps you'd like one too. And when you're ready for the last section on Le Chatelier's principle, come on back. We're going to work to upset the equilibrium. We'll talk about stressing, and we might be facing that ourselves. So I'm going to stop the video. Come back when you'd like to complete.